All righty, let's go ahead and get started for today. Well, today we're going to move on. We're going to continue with fluids, but move on to a different kind of topic as it pertains to fluids. However, before I get to that, just a reminder, the homework for this particular topic, or what we just finished, that is Bernoulli's equation type stuff, is on Canvas. Don't forget about that. I believe it's due on Wednesday. So be sure you're working on it if you haven't already submitted it. And I guess along with that, are there any questions about what we've done in the previous couple of lectures, talking about Bernoulli's equation and the continuity equation, how to set those types of problems up, anything like that? All right. Well then, with that said, let's go ahead and talk about the next part of fluids, which is basically going to be buoyant force and Archimedes principle. Okay. Now, the buoyant force is an interesting concept. I'm sure most people have heard the term buoyancy, where something is buoyant, or even a buoy out in the water. And all it is a kind of a measure of how well something floats. That's a good way to think about it. If something is floating in a liquid or a gas, then it's buoyant, okay? And the more buoyant it is, the better it will float. And, you know, you have some things that actually float on the surface of a liquid, but then you may have other things that sink down a little bit, but not all the way. You have other things that sink all the way down like a rock, and everything in between. You can have things that sink, but sink very, very slowly. And so these are different measures of the buoyancy of those objects. And as I said, the more buoyant, the better it floats. But what is it that makes something buoyant? What is it that allows something to float? Because, I mean, if we consider, for instance, a cup here with some water in it, and I put an ice cube in here, the ice cube floats. But what's going on? I mean, the ice is in gravity, right? The cup's in gravity, the water's in gravity, so everything falls down as far as it can go. This cup is on a tabletop. The liquid is at the bottom of the cup and fills up as high as it can go. But the ice is not falling, it's floating. Gravity is sitting there, mg, trying to pull this thing down. And so, of course, we know from first semester physics that if the object isn't falling by gravity, then there must be some other force acting on it, which is opposing gravity. I mean, that's fairly intuitive, but it's true to say. Gravity is a force pulling down on this, just as it pulls down on all objects, but this particular object isn't falling. Thus, there must be a force acting in opposition to gravity, which is preventing it from falling. And that force is called the buoyant force, okay? Buoyant force is the force which is basically going against gravity. So I call it FB, buoyant force, pushing up. But how does this, what is this force? Where is it coming from? Why isn't there a buoyant force on me when I'm just sitting here in my apartment? I mean, I fall down, I'm on my chair, I'm sitting down right now, I'm not floating up into the air. But why is this ice able to float, but something like a rock falls down all the way to the bottom of the liquid. Why does one feel the buoyant force, but the other doesn't, seemingly? Well, the answer is they all feel a buoyant force. Every single object feels a buoyant force when it's placed in a fluid. The ice is feeling it and the rock is feeling it. It's just that for whatever reason, the buoyant force that acts on the ice is sufficient to oppose gravity, whereas the buoyant force that acts on the rock is not. Now, that could mean several things. Either the buoyant force is the same amount on both objects, but the rock is heavier than the ice. And so the buoyant force isn't big enough to overcome the weight of the rock, but it is big enough to overcome the weight of the ice. That's one possibility. Another possibility is that each object feels a buoyant force, but the size of the buoyant force changes based on something about the object. Maybe ice because it's water, and water has a certain buoyant force, whereas a rock has a different buoyant force. Or maybe the more mass an object has, the less the buoyant force is. Or maybe it's the size. Maybe larger objects have a higher buoyant force and smaller objects have a smaller buoyant force. These are all different possibilities which may explain what's going on here. So let's investigate what's really going on. Well, one thing we need to understand is something I mentioned in the previous class, and I'm sure we've all heard of in some form, which is as an object sinks or goes down in depth of a fluid, the pressure acting on that object goes up and up and up. It gets higher. So, for instance, let's say we have, here's a pond or a lake or something. There's the surface of the lake, and we have an object. Here's my object. Underneath the water, okay? And I know that the object is a certain distance, a certain depth, I'll call it H1, underneath the surface, okay? Well, one can ask, how much pressure will this object feel due to the fluid? Well, in order to ask that, we first must understand that there will be a pressure felt by the object due to the fluid. But that's pretty intuitive. If we think about what's going on when we have this object and I place it in the water, well, the water had to kind of move out of the way to make room for the object, right? Before I put the object there, it was all water. Then I placed this box in under the water. Well, where the water was has now moved and I've put a box there. But that the water doesn't like that. It wants to go back to the place it was before. So you'll find that you'll have the water trying to go back. And so all the water is pushing back on this object, okay? It's pushing from the left, it's pushing from the right, the top, the bottom, in every direction. The water is trying to squeeze this object. And we know that the definition of pressure is the force felt by an object divided by the area over which this object feels the force. Remember the example of the bed of nails. If you lay down on a bed of nails, you're okay, but if you lay down on one nail, that's not a good thing. It's the same amount of force being applied. It's just that with the bed of nails, that force is applied over a whole bunch of nails. So each individual nail only applies a little bit of force. Whereas if you only have one nail sitting there, then all of the force is being applied by that one nail. And so you get punctured. So there's pressure involved here. There's a force due to the water trying to squeeze this object, and it's squeezing over the whole size of the object. Okay. And I know why the water is squeezing. For instance, you can think about a column of water over the top of this box is trying to be pulled down by gravity. And so all of this water here is pushing down. And the same thing would go here. All of the water on the side is pushing that way, all of the water on this side, and so forth. And then, of course, from the bottom as well. Well, it turns out that the amount of pressure you feel based on how deep you go into the water is given by a very easy equation. And it is, we've seen it in Bernoulli, actually. The equation is the pressure at a certain depth, okay, a certain amount you go underwater, is given by rho, and that's the density of the fluid. So of course, this is going to depend on what kind of fluid we're in. Are we in the air? Are we in water? Are we in honey? Are we in jello? What is this thing we're in? The thicker or the heavier the fluid, then I would expect the more pressure it's going to apply to me. Whereas a thinner fluid like air won't apply as much pressure. So it should depend on the density of the fluid we're talking about, times G. And you see this rho times G, that's kind of like mass times gravity. It's kind of like a weight. It's not exactly weight because it's not mass, it's density, but it's kind of like a weight. So it's how much water, the weight of the water being applied to you, times the depth. And in this case, we call the depth H, which is like height, but it's rho GH, how much pressure you feel because of how deep you are under the water. Okay? The deeper you go, the more pressure you feel because there's more water on top of you pushing down on you. That's one way of thinking about it. And so that's the important equation. This is the pressure-depth relationship. The deeper under the water you go, the more pressure you're going to feel. How much pressure do you feel? It's given by rho times G times H. And so you see where that term from Bernoulli came from. It's a term about the pressure in the fluid due to how deep the fluid is, or how high it is, or how low it is, or whatever. So if we think about this being the amount of pressure that my box in my example here is going to feel, well, notice that the size of the box means that the top of the box is at a different depth than the bottom of the box. Right? The top of the box is not as deep as the bottom. But if the pressure depends on how deep you are, that means, seemingly, that since the bottom is deeper, it's going to feel more pressure than the top. Now the sides, the left side of the box and the right side of the box, they're at the same depth. So all the stuff here cancels out all the stuff here, right? The amount of pressure pushing from the left is the same amount as the pressure pushing from the right. And so if I stick my object under the water, it's not going to be moving to the left for some weird reason. Okay. Now, of course, if there's a current, if the water is moving, then it's going to move the object too. But if I just have a nice still pond and I throw a rock in the pond, the rock's just going to fall down. It's not going to move to the left or move to the right. And that's because the pressure under the water is balanced from left to right. However, top to bottom is not balanced. How do I know? Well, let's take a look at the top here. At the top, the pressure at the top is going to be rho times G times the depth 1. Depth 1 being the top of the box. Okay, how deep the top of the box is. Then we can have a different depth, which is from the surface down to the bottom of the box. And let that be called H2. Now, H2 is going to be whatever the depth to the top is, plus the size of my object. So if the size of my object here, we'll call it, I don't know, delta H. This is kind of how math people do it. The top of the box is H1. The bottom of the box goes down to H2. And H2 is H1 plus the size of the box. And I call the size of the box delta H. So if this is true, then the pressure at the bottom is rho GH2, which is, oh, let me finish writing this, plus delta H. So rho GH2 is rho times G times H1 plus rho times G times delta H. And so you see the pressure at the bottom is the same as the pressure at the top, plus some extra bit. Because it's lower, the bottom of the box is deeper than the top, so it feels more pressure. So that means the bottom will feel more pressure than the top. And if we remember from Bernoulli, airplanes fly because the pressure on the bottom of the wing is higher than the pressure on the top of the wing. So there's excess force pushing up, and so the thing can fly. Well, the same thing goes here. Because the bottom of the box is deeper than the top, the bottom feels more pressure than the top. So there's more force from the bottom pushing up than there is from the top pushing down. And it's given by that little bit, whatever this is. And this pressure relates to the buoyant force. They're not the same thing, but the buoyant force is due to that extra pressure. It's just that pressure is not force, it's force over area. So if we multiply by the size of the object, we multiply by its area, that would tell us the buoyant force. So you can think of the buoyant force as being this rho times G times delta H, which is the pressure, the extra pressure at the bottom, times whatever the area of the bottom of the box is. Okay. Whatever that is, don't worry about this. This little equation here is not important, but the concept of it is. There is some extra force pushing up on this object because there's more pressure at the bottom than there is at the top, and so we can convert pressure to force. And that extra force from the bottom, we call buoyant force. And then the object will float if this buoyant force is bigger than the weight pushing down on the object. Because remember, this whole time, we have mg trying to pull this block down the whole way. However, there's this extra buoyant force sitting there. Now, the buoyant force might be very big, it might be very small. If it's very big, then the buoyant force might be bigger than the weight. If the buoyant force is bigger than the weight, then you have a buoyant force pushing up, weight pulling down, but the buoyant force pushing up is bigger. So the net force is upwards, and my object will be pushed up to the surface, thus it's floating. If the buoyant force, for whatever reason, is very small, then it's not as big as the weight. So you have the weight pulling down, a little bit of buoyant force pushing up, but it's not enough. So the net force is down, and the object will fall, and thus it sinks. Those are the two options. Of course, there's the extreme, which is the buoyant force happens to be exactly equal to the weight. And if that's the case, then when you put an object under the water and you let go, it just sits there. It doesn't float to the top. It doesn't sink to the bottom. It just stays sitting there in the water. But that's, that's a rare thing, that the buoyant force and the weight happen to be identical. All right, so are there any questions about this concept, the conceptual view going on here, why an object could float instead of sink and so on?
I have a question about the equation.
Yes, ma'am.
What's the A?
Yeah, the A is, remember, pressure is defined to be force over area. Okay, and so if I want the force, then I just solve this little equation. Force is the pressure times the area, where the area means, if you have a big old window, then there's a lot of area here for things to push on. If you have a little bitty window, then there's only a little bit of area. And so the area relates to how big the object is. So if you have a little bitty, I don't know, boat, or a very, very huge boat, well, the very big boat probably weighs more, but at the same time, it's also larger, so it has a bigger area. And for the small boat, it may not weigh that much, but it may have a very small area. And it's the combination that has to do with pressure. Pressure is force and area together. And so the buoyant force, if I want force, well, this part is the pressure. Remember, this equation right here tells me the pressure. So if I want to convert that pressure to a force, I have to multiply by the area of the object that this pressure is being applied to. Okay, so that's what this A means. It's, like I said, this equation up here, that's the equation we're going to be using to calculate things. Okay, this is just kind of so you can see what the buoyant force kind of means. The buoyant force arises from the fact that the bottom of the object will always have a bigger pressure than the top. And so we can convert that extra pressure from the bottom into a force acting on the bottom. And in order to do it, we multiply by area. Okay, so does that make sense?
Yes.
All right, any other questions?
To calculate the area, is it still pi times r squared?
No, it would depend on the object, which is why I'm not putting, any real specifics here. If you have a cube, if this is a box, then the area would be length times width, the size of the face of the box. If it's a sphere, then you have the surface area of a sphere. If it's a pyramid, if it's a boat, different things have different ways of measuring the area. We're not going to use this. We're not going to have some weird object and I'm going to make you calculate the area and do all of this stuff. Rather, what we're going to do is kind of the more fundamental thing, which is to say, I put a person dives down 100 meters. What's the buoyant force, or how much pressure does he feel? And so you're just going to say, well, I know an actual person, his head is higher up than the legs. And so we have the pressure at the head versus the pressure at the legs. We're not going to worry about that. I'm only introducing it here to show why there would be a buoyant force. Once we know there's a buoyant force, then we're just going to say, what's the pressure of an object at this depth? And we don't have to worry about converting areas or anything like that. So to answer your question, if we were doing something extremely detailed, where we actually wanted to find the difference in pressures between the top of an object and the bottom, then yeah, we would have to figure out how to calculate the area, and the area would depend on the shape of the object. It may be a square-shaped object. It may be like an ellipse, like a fish shape or something. And then you get into, calculus and how to calculate the area of weird shapes. For our purposes, we won't worry too much about it. Any other questions? All right. Now, another thing to note about this, if we're going to investigate this concept, first of all, what did we learn? First thing we know is when an object is in a fluid, the deeper it goes in that fluid, the more pressure it's going to feel. Thus, if you dive down in an ocean, you have to be very careful, because the deeper you go, the more the water is going to squeeze you, and eventually you'll die. You won't be able to open your lungs to breathe if you have scuba gear on, or your mask will literally shatter. Or if you're in a submarine, well, eventually you could go so deep that even the submarine itself would be crushed by the depth. Okay, which is what makes some of the deep sea creatures really amazing. That, you know, when you see videos on the Discovery Channel or things like that of like the giant squid that lives extremely deep in the ocean, it looks like it's just normal, right? It just looks like a squid or some of the fish or jellyfish or things. But you have to remember when you're looking at these things that the pressure that's squeezing those animals is intense so much that we as humans would not survive. But they evolved over time to live in that kind of environment. And if you were to take that jellyfish from extremely deep part of the ocean and bring it up to a shallow part, well, the thing could explode because its body was formed to withstand a huge crushing pressure, trying to, squeeze it. Well, if that pressure isn't there anymore, then whatever mechanisms the body had to not be crushed is now working against it. And so it had actually exploded its body because there's not enough pressure keeping it closed. Or one of the big things everybody, I'm sure, has heard of is the bends, which is a dangerous thing that scuba divers have to confront, which is if they dive too deep or if they dive deeply and they do their thing and then they, for whatever reason, they have to come up really quick. Well, this is a dangerous thing because your body acclimates to being at a high pressure. And if you come up too quickly, then you're changing the pressure on your body too fast, not slow enough for your body to kind of do it gradually. And you have extremely bad side effects, like nitrogen bubbles that are in the blood start to boil off. And that's one of the things that's extremely painful for scuba divers if they do this type of thing. And we're not talking about, a mile under the water. We're talking about, 100 meters, 200 meters, not that deep. You can have really bad side effects. And it's all because of this extra pressure that you're going to be feeling the deeper and deeper and deeper you go. So that's the first thing we know. The deeper you go, the more pressure you're going to feel. And it's given by that simple equation, rho GH, very easy. And we now know that when an object is in a fluid, because of its size and the fact that it will always have, unless it's flat, it will always have the top and the bottom of the object at different depths. Thus, there'll be different pressures. You will always have a buoyant force acting on an object. Sometimes the buoyant force is enough to overcome weight, and thus the object will float. Sometimes it's not, and it'll sink. But no matter what, there's always some amount of buoyant force, which means if you were to measure the weight of an object that's in a fluid, it will always weigh less than it does just in the air. And I'm sure we've all experienced this if you've ever gone swimming and you're in the swimming pool and you're going around for a while, you just get used to being in a swimming pool. If your feet are on the ground, you could jump up pretty high, stuff like that. But then you go to get out, so you pull yourself up on the side of the pool to get out. Well, as you start pulling yourself up, it's easy. But then as you get more and more out of the water, all of a sudden you feel heavier and heavier, and it's harder for you to pull yourself out. Okay. The reason is because when your body's in the water, there's that extra buoyant force trying to push you up, working against your weight. Thus, the amount of force you have to pull to get yourself out of the swimming pool is not as much because you're being helped by the buoyant force. But as you start to get more and more out of the swimming pool, less of your body is in the fluid. So you have less buoyant force helping you. And so you feel more and more heavy the more you get out of the pool. And so this concept is what's called the apparent weight. Apparent weight of an object. Okay, and all this means is if you were to weigh an object that's in a fluid, it will weigh less, but you don't know that. Let's say you just, I don't know, you're captured by aliens or something. You go to their home planet, you wake up and you weigh an object for whatever, you're doing an experiment. And you weigh the object and you get a certain amount of weight. Fine. Then you find out, wait a second, this alien environment I'm in is some kind of a fluid world. I'm in a water world or something. And so the weight that I measured, no matter what experiment I do, I'm always going to measure this weight because there's always the buoyant force acting on that object. But if I take the object, take it out of that fluid world and measure it on Earth, let's say the gravity and all of that is the same for both planets, then the weight all of a sudden is a lot more. And it's purely because when you measure the weight of an object in a liquid or in a fluid, it will weigh less than it does when it's not in that fluid. And so we call it apparent weight because apparently that's the weight unless you know better. You know, the true weight is what its actual weight is, m times g. The apparent weight is what you measured it to be while it was in the fluid, which is going to be different. And so this is one thing we may want to calculate. We may want to say, look, we're doing some experiments for these deep sea divers. They want to go, I don't know, rescue some buried or some treasure that was on a sunken ship. And we happen to know there's a chest of gold down there. And I know how much gold is in there. So I know this chest of gold is going to weigh 500 pounds. However, that's what it weighs when it's on the surface of the earth. How much would it weigh when it's under the water? If I were to try to lift it as a diver while I'm underwater, how heavy would it feel to me? That's what the apparent weight would be. So what is it? The apparent weight apparent, is the true weight of the object. So if you were to measure its weight, m times g, this is what you'd get, minus the amount of force that's trying to lift the object because it's in the fluid. That's called the buoyant force. Right? So if you're in the water, let's say you weigh 200 pounds, just as a round number. You weigh 200 pounds, you get in the water, and someone may ask, how heavy would you weigh if I were to put a weight scale underwater and you stood on it? Well, the weight scale would say is this number here, the apparent weight, and you could figure out what it would be. You say, if I know what the buoyant force is that's acting on me, which we'll figure out how to see that in a second, when we get to Archimedes' principle, I should say. Well, all I have to do is, if I know the mass, I know what my mass is, or I know my true weight is to 200 pounds, minus whatever this buoyant force happens to be. And like I said, an object floats if this buoyant force is bigger than the true weight. An object sinks if the buoyant force is less. But no matter what, the apparent weight is always less than the true weight. So an object in a fluid will always feel lighter than an object in the air. So this is another equation we need. There we go. So we have two big equations right now. And I'll rewrite them here. The first, the pressure on an object due to its depth is rho times g times h, where rho is the density of the fluid. G, of course, is 9.8 while we're on Earth. Now, these same calculations can be done on a different planet. Let's say you're an astronaut and you're doing experiments on Mars, and you dig down a little bit and you find water under the surface of Mars. And you want to say, well, what pressure would I feel if I were to dive under the Martian water? Well, instead of 9.8, which is the acceleration due to gravity on Earth, you use whatever the acceleration due to gravity on Mars is. Now, obviously, in this class, we're just going to be talking about the Earth. So we always use 9.8 for it. And then, of course, H is the object's depth. How deep is this object currently? So that's the first big equation. The next is the apparent weight of an object under the water or in a fluid is the true weight minus the buoyant force. And by true weight, I mean m times g minus buoyant force. Okay. So those are our two big equations for now. We're going to get a few more as we discuss Archimedes' principle. But before I get to those, of course, we want to make sure we understand these. So as an example, how would we use these? Here's a question. A diver whose mass is 100 kilograms dives to a depth of 200 meters. Calculate the pressure the diver would feel and his apparent weight. Assume the buoyant force is, let's say, 300 newtons. Okay. All right, so one thing you need to know, which is always going to be true for this class, so it's easy to remember, the density of water is 1,000 kilograms per meters cubed. So there's our example. Diver diving down. We know how what his mass is. Dives down a certain distance. I want to know what kind of pressure would he expect. And the reason, of course, is we want to make sure it's not too deep to kill him. And if it is too deep, then we want to make sure we outfit the diver with special equipment to allow him to survive big depths. And then, of course, we want to know how heavy would this diver feel if we were to weigh him while he's at this depth. All right, so firstly, part A, in order to calculate the pressure on an object due to its depth, it's very easy. Pressure is rho times G times H. Rho, we're assuming the diver is diving in water, is 1,000. G, that's 9.8. And then H is the depth. Well, the depth of this particular diver, we're told, is 200 meters. And so we just calculate this out, 1,000 times 200 times 9.8, and we get a pressure of 1.96 times 10 to the 1, 2, 3, 4, 5, 6 pascals. Now, is this a lot? Well, I can tell you, I believe the pressure that you feel just sitting out in normal everyday land, there you are sitting in your table or your chair, whatever, the pressure in the atmosphere is about 1.01 times 10 to the 5th pascals. So this person is feeling 2 times 10 to the 6th, basically. So that's like 20 times the amount of pressure that they feel just normally on Earth. That's a big amount of pressure. All right, part B. We want to know, what would the person feel? How heavy would the person feel while they're at this step? And we're told, because we don't yet know how to calculate the buoyant force, I say just assume the buoyant force is this number. All right, well, I know the apparent weight is the true weight, oops, minus the buoyant force. True weight, of course, is m times g. And the buoyant force, we're told, is 300 here. M times g, we're told the diver has a mass of 100. So it's 100 times 9.8 minus 300. So 980 minus 300 is 680 newtons. Okay, so certainly they feel less than their true weight. They feel lighter. By how much? Well, about 2/3 as heavy as they normally are. So they feel a third lighter. And there we go. Yeah.
So the true weight formula is the m times g.
That's right. Right. It's the same equation we got in first semester physics. Whenever you talk about the weight of an object, it's the object's mass times gravity. And so that's the true weight.
And what does this at, like, under the 300 newtons? What does that say?
Here, you mean?
Yeah.
Yeah, that just is relevant to this. This is just letting you know, so you can see what the heck does this 1.96 times 10 to the 6. So, what does that mean? Is that big? Is that small? I don't know. That's just telling you that the pressure in the atmosphere, so it's ATM, the pressure of the atmosphere is 1.01 times 10 to the 5th. So every object, you sitting there in your chair, the air around you is squeezing you with a pressure of that much. And so this calculation tells us this person, since they dive down in the water, feels 20 times more pressure than you do sitting in the air. And so it's just a way of kind of getting a grasp of if this number is a big number or a small number. Any other questions about this? All right, well, I'm going to go ahead and leave it alone for now because we're almost out of time. But I will say one thing to look forward to in the next class is, of course, actually talking about Archimedes' principle, which deals a lot with buoyant force, but also something else that will become important, and especially like as we talk about divers in the water and things like that, is what's not as important is like this number we just calculated, the pressure the person feels. That number is not all that important. What is important usually is not the total pressure, but rather what's the difference in pressure. Like everything feels the pressure of the atmosphere, right? So I don't care that this thing feels that much pressure. What I care about is how much more than they normally feel. And a way to think about it is, for instance, if you think about you're driving your car and you have a flat tire. And so you get out and you look at your tire and it's flat. Well, and then when it's full, of course, you fill it with air to a certain pressure. And so the air inside the tire, there's a certain pressure, and that's what keeps the tire, open or filled with air, let's say. Well, when it's flat, it doesn't mean there's no pressure. There's no air in the tire. There is air in the tire. It's just that the amount of air is the same as the amount of air outside the tire. It's just the atmosphere. And so a tire pressure what a tire feels, even when it's flat, is still some amount of pressure. But if you go and put your air pump, you plug it into the tire, and you look at the little gauge that tells you how much pressure there is, it would say 0 pressure. But you know, just by your own intuition, that it can't be 0 pressure. The atmosphere is pushing on it, so there's this much pressure at least. And this is a concept called gauge pressure. Gauge pressure. And that is a lot of times what you see when you're actually doing things with pressures. Whenever you pump up a bicycle tire or a car tire or things like this, or a basketball or a football, there's always a little gauge that tells you how much pressure how much air is in the thing. And it always starts at 0 when the thing is empty. But we know it's not really 0. It's actually the pressure of the atmosphere is still there. So what these objects do, what these pieces of equipment do, is they say, look, no one cares that the atmosphere is there because it's always there. Every single object on Earth, no matter where it is, feels atmospheric pressure. What does matter is how much more than the atmospheric pressure is there. And that's the concept called gauge pressure. And so what we're going to do is modify what we did in part A here. Instead of calculating what pressure the diver feels, what I'd like to do is figure out what would the scuba gear say the pressure is. The scuba gear would not say this number we just calculated. What the scuba gear would give us is the gauge pressure. This is what's called absolute pressure. The gauge pressure is how much more pressure is there due to these circumstances. And so we'll figure out how to do that. It's really easy. It's just like the apparent weight is the true weight minus some amount. Well, the gauge pressure is the absolute pressure minus some amount. Okay. So we'll discuss that next time and then get into Archimedes principle, which is all about buoyant force and things like that. So that's what we can expect for next time. Don't forget the homework problem on Canvas is there. Also, I had forgotten, and I thankfully was reminded by a student to post Friday's lecture on Canvas, but it's posted now. Just right before class, I uploaded it to YouTube, and so it should be done doing whatever YouTube has to do to get it onto their website by now. So that's there. I'll be, of course, uploading this lecture as always as well. So if you want to go back and look at stuff or get examples to help you do the homework, that's the best bet for that. Anyway, other than that, you're free to go. If you have any questions, let me know, but I will see you next time.
Have a nice day.
All right, you too.